this video, we'll just talk about a few of the milestones from the history of AI, picking up from about the 1950s, shortly after the first electronic computers were built. So confidence was pretty high going into this project. So this is a little abstract from the proposal for a conference, a 2-month-long conference with some of the bright lights of the early AI movement, where they were planning on doing some artificial intelligence research. So check out the level of confidence that these guys had. We proposed that a 2-month, 10-man study of artificial intelligence be carried out during the summer of 1956 at Dartmouth College in Hanover, New Hampshire. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. An attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. We think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer. Huh? They figured they could knock this out in a summer. Right? That's astounding levels of confidence in how much progress could be made on artificial intelligence in 1956. At that 1956 conference, and this might help to explain why they were so confident, Herbert Simon and Alan Newell and John Shaw presented a program that they had written called the Logic Theorist. So if you could do some types of, it could do some types of the problems that you would encounter in a standard, say, intro to logic course. So this is an image of a derivation, a logical derivation. The point here is that you are given some premises, those are the top 3 lines, and then following the rules of logic, you derive some conclusion. That's the bottom line. So they created it by having undergraduates talk their way through a logical derivation and programming into a computer some of the moves and the strategies that they used. So if you think, I think you can see here a hint of why they were so confident, because of the type of problems that they started with. So doing logical derivations is hard. It's genuinely challenging. If you've taken a course in logic, this image might be giving you horrible memories of how difficult it can genuinely be. But in the standard logical system that they were using, this is just simple, first order predicate logic. There are an extremely small set of rules that you're allowed to apply. There's like a dozen rules or something like that. And the conditions of success are extremely well specified. You've either derived a thing according to the rules of logic or you didn't. And you know for sure when you've done it and when you haven't. So the type of problem that they're dealing with is something that looks a lot like intelligence, right? You need pretty decent intelligence to be able to do this problem. But it's a very particular type of intelligence that they were trying to simulate. This confidence was robust, let's say. So here, one of the designers, Herbert Simon, one of the absolute pioneers of AI and cognitive science, he said in 1956, machines will be capable within 20 years of doing any work that man can do. So 20 years from 1956 is 1976. They didn't quite get there. We're still not there. But I suspect that because of the type of problems that early AI research started to tackle, this looked a lot easier than it was going to turn out to be. Newell and Simon tried to generalize this, right? So doing logic problems it requires intelligence, but of course it isn't the sum of intelligence. So what they wanted was to create a general problem solver, which they abbreviated with the now unfortunate GPS. The idea was to create general strategies that could be applied to any type of problem. So they used the kind of core computational structures of the logical theorist and tried to build a computer that could play chess. Again, just note that chess is a lot like logic in the sense that the rules of chess are pretty straightforward to specify. You specify the initial conditions, the original board setup. You specify the goal conditions, that is getting your opponent in checkmate, and how the pieces can move. And once you've done that, it's a few dozen rules, you've specified the whole game of chess. And you can do it in a very precise, very formal way that is not easy, but relatively straightforward to program into a computer. So that was a line of research that got going in the 50s, continued on into the 60s, the 70s. You'll notice that we didn't get a general problem solver, but attempts continued. So the real problem, and the thing that would have impressed Descartes, was not playing chess, but using language in a natural way that shows that it understands meaning. So turns out to be a lot harder. The difference between simulating intelligence and real intelligence is much starker in the case of using language. So consider ELIZA. ELIZA was a program developed in the mid-1960s, and it does a reasonable job, especially for the 1960s, of simulating natural language. So we've got a short little conversation with ELIZA here. ELIZA pretends that it's a therapist trying to ask questions about you and how you're doing. So, ELIZA says, "Is something troubling you?" And you say, "All men are alike." And ELIZA says, "What is the connection, do you suppose?" "They're always bugging us about something or other." "Can you think of a specific example?" "Well, my boyfriend made me come here." "Is it important to you that your boyfriend made you come here?" "He says I'm depressed much of the time." "I'm sorry to hear that you are depressed." "It's true, I'm unhappy." "Can you explain what made you unhappy?" That's pretty good, right? Especially for the 60s. That's it sounds like it's listening and responding in meaningful ways to what's being said to it. You can try this for yourself. There's lots of versions of ELIZA online if you want to have a little chat with it. I had this little chat with ELIZA just the other day, and I think it becomes pretty clear ELIZA's not really understanding what you're saying. So ELIZA says, "Hello, I'm ELIZA." I say, "Hello, ELIZA, how are you?" Would I prefer if you were not what?" says ELIZA. And at this point, I'm confused. We were discussing you, not me. I say, "I was just being polite." ELIZA says, I see. I ask, "I'm wondering if you understand language." ELIZA says, "Do you believe it is normal to be wondering if me understand language?" At this point, I think it is normal. I'm starting to think you don't." "How long have you been starting to think me don't?" "Oh boy." And ELIZA says, "Okay, I'm starting to think me don't. Tell me more." Not what I would call one of my more engaging and enlightening conversations. So ELIZA's clearly simulating the ability to understand language, not really having it. We've got another example here, SHRDLU. Sounds like it stands for something, doesn't it? But it doesn't. It's just a name that they typed in all caps for some reason. So developed in the late 60s and early 1970s at MIT, SHRDLU had a little simulated world. So if you can see this image, there's little blocks and triangles and stuff, and you can talk to SHRDLU, type out conversations with SHRDLU, and ask it to do things in its little simulated world. If you keep it really straightforward and simple, SHRDLU can understand you and perform those tasks. So in this image, we've got pick up a big red block, and SHRDLU says, "Okay." You can see the high technology display here. The red block has a little red on the bottom left corner of it. So here's a typical conversation with SHRDLU. So a person says, "Pick up a big red block." Computer says, "Okay," and it does it. Person says, "Grasp the pyramid." And SHRDLU says, "I don't understand which pyramid you mean." Perfectly reasonable request for clarification. Person says, "Find a block which is taller than the one you are holding and put it in the box." Computer says, "By it, I assume you mean the block which is taller than the one I am holding." "Okay," and it does it. And the person says, "What does the box contain?" The computer says, "The blue pyramid and the blue block." Hey, that's not bad, right? But again, what we've got here is a computer that's perfectly able to operate in a pretty narrowly specified linguistic context. If you start going outside of the scripts that SHRDLU is able to deal with, it appears unintelligent pretty fast. So here's another conversation quoted from Hauslin's book, Artificial Intelligence, The Very Idea. Somebody says to SHRDLU, "Trade you a squirt gun for a big red block." SHRDLU says, "Sorry, I don't know the word trade." Person says, "A trade is a free exchange of property." SHRDLU says, "Sorry, I don't know the word act." Acts are what people do on purpose, not by accident." "Sorry, I don't know the word people." Person says, "Sorry, I thought you were smarter than you are." And SHRDLU says, "Sorry, I don't know the word sorry." So again, it's pretty obvious that SHRDLU's working on a script. SHRDLU's acting mechanically, not meaningfully. So again, we're in the 1970s and we're nowhere near meeting Descartes' challenge of, he thinks it's conceptually impossible that a mechanism could deal with language in a meaningful way. As of the 70s, I think that's pretty clear that that's not true. Despite this limited success, confidence remains sky high in the artificial intelligence project. Marvin Minsky says in 1967, within a generation, the problem of creating artificial intelligence will substantially be solved. Again, no, not even a dent in their confidence at this point. Okay, so the examples I've shown you so far come from what's called the symbolic AI tradition, where formal rules are applied. The rules of chess or the rules of logic. SHRDLU and ELIZA are both using formal scripts. So if you get this type of input, make this type of output. But all along during this time, there was another tradition of trying to do simulated intelligence alongside this one. And this is the earliest version of that, the Perceptron. All right, it's good, right? So in the 1950s, funded by the US Navy, Frank Rosenblatt developed the first perceptron, the first iteration of what would become artificial neural networks. So if you've heard of deep learning or machine learning, that almost inevitably runs on one of the distant ancestors of this perceptron. So input to the perceptron would come from a digital camera with about 400 input pixels, so 20 by 20, not megapixels, 400 pixels. Sort of photoelectric cells that would take in one little block, 20 by 20. The inputs would then go to a artificial neuron, which was a quite simple structure. It would just sum up the inputs, and if the total went above a certain threshold, it would output a 1. If it was below a threshold, it would output a 0. So the inputs would be weighted. So if you see X1 and there's this line with W1, W1 is a weight on that, and those weights are how you adjust the perceptron. So in the beginning, it was literally hand adjusting those weights. Eventually, it becomes a software problem rather than a hardware problem, but you adjust the weights on those connections from the photovoltaic cell to the artificial neuron. And if you adjust them just right, the perceptron can, in fact, do some categorization tasks. So it's the Navy doing this. They have in mind military categorization tasks, like, is there a tank in this picture or isn't there a tank? And you could get it to do some of this stuff, right? You could get it to successfully, if you tune the weights just right, you could get it to do some categorization tasks. Famously, it wasn't doing it, however, in a way that looks at all intelligent. So here's an example again from Marvin Minsky describing early perceptron research. So he says, the perceptron, was looking at a scene of a forest in which there were camouflage tanks in one picture and no camouflage tanks in another. And the perceptron, after a little training, made a 100% correct distinction between these two different sets of photographs. They were embarrassed a few hours later to discover that the two rolls of film had been developed differently. And so these pictures were just a little darker than all these other pictures, and the perceptron was just measuring the total amount of light in the scene. But it was very clever of the perceptron to find some way of making the distinction. So perceptron was able to successfully categorize things, but it didn't always do it in the way that you might want it to. In this case, one roll of film was developed slightly differently. It was all of the pictures of, say, tanks were a little bit brighter than all of the pictures with no tanks, and it just picked up on the brightness rather than the presence or non-presence of a tank. I take it artificial intelligence, so modern neural networks are much more sophisticated. They still don't seem to be able to tell whether there's a car in a picture or not. That seems to be something that we have to sort of feed to them. So for this and some more technical reasons I won't get into, enthusiasm for artificial neural networks dropped off pretty substantially for a few decades. It's sometimes referred to as the AI winter. So from like 1975 to the early 1990s, enthusiasm for artificial intelligence research really dropped off because the results just weren't coming in especially compared to the level of enthusiasm and confidence that we saw in the 1950s and the 1960s. But based on some theoretical work in the 1970s, the 1980s saw the slow development of what's called deep neural networks. So these are neural networks. Perceptron just had one layer. What people realized was adding in a couple more layers really enhanced the abilities of these neural networks. For a lot of tasks, artificial neural networks have gone a lot further than the traditional symbolic computational model. This is a picture of Deep Blue. This is a computer designed by IBM to play chess. So Deep Blue used what you might call traditional symbolic manipulation design, essentially doing a deep search of all the possible chess games coming up and scoring those according to rules derived from a great big database of past chess games played by chess masters. So in 1997, Deep Blue played against then world champion chess player Garry Kasparov, beating him 3-2 with one draw. So this was, for my money, kind of a high watermark in the traditional symbol manipulation model of computation. This was an incredible win. It really revived interest in artificial intelligence in the popular imagination, but they didn't get much further with the traditional, rules-based model of artificial intelligence. Compare that to where we are now with AlphaZero. So AlphaZero is one of the most recent generations of chess-playing AIs, and it uses a combination of rules and neural net architecture, which is more or less the sort of standard of how AI works now. It wasn't given a huge archive of games to play. It was actually just trained up by having it play games against itself and adjusting the weights in its neural network according to its success or failure on either side of the game. Within a day, 24 hours of this type of training, it was better at chess than any human in history. Chess masters have a rating system to rank them quantitatively. So the best chess player in the world right now, Magnus Carlsen, has a rating of 2,862. Deep Blue is estimated to have a rating of something like 2,700. Garry Kasparov was also rated in the 2,800, but might have lost because of the unusual playing style of Deep Blue that he wasn't used to yet. But AlphaZero's rating is estimated to be in the mid 3,000s, like 3,500 in there, which is literally better than any human who's ever played the game. It's an incredible advance using this kind of neural net architecture. It's impressive, right? So the question is, where does this get us with the good old Turing test? Since there have been these amazing advances in a whole bunch of parts of artificial intelligence, I mean, it just did chess. There's a million other examples. Surely we've got a computer that can pass the Turing test, right? And therefore defeat Descartes, right? Therefore show that mechanical reasoning is not actually a paradox, that it's a real possibility. So far, no. So far, there is no computer on this planet that can consistently fool a person into thinking it's a human. While we continue to make amazing strides in performing very clear, well-specified tasks, there's still no computer that can operate in the kind of messy, ambiguous world of human language to the degree that a normal person can. So enjoy this while it lasts. Maybe you're the only kind of being on the planet that can read a paper and summarize it in a short paragraph in a way that is clear and meaningful. You're the only thing on the planet that can hold a conversation with another being and have it be convincingly meaningful to the other person for an extended period of time. I plan to enjoy this while it lasts. It might not last forever, but currently we still haven't met Descartes' challenge of showing that reason can be made mechanical.